Good morning to all. Today we'll discuss vibrational spectroscopy or infrared spectroscopy or IR spectroscopy. This is the outlay of our second unit. Within that is the vibrational spectroscopy topic. We have to see the normal modes of vibrations and classification of vibrations, vibrations of polyatomic molecules, that is linear and non-linear molecules, determination of force constant. Okay, these are the topics we are going to discuss. The vibrational spectroscopy. Under the vibrational spectroscopy, the topics which we are going to discuss under this lecture are this. The selection rule for IR spectroscopy is the molecule should not have zero dipole moment. If the induced dipole moment or permanent dipole moment is there in the molecule will be giving, or it will be IR active. That means that molecule will give IR spectrum. The selection rule for the vibrational spectroscopy or IR spectroscopy is molecule dipole moment should not be equal to zero. Either this dipole moment is either permanent dipole moment or induced dipole moment. What is meant by induced dipole moment? When you pass the IR radiation on sample, the sample should induce the dipole moment. That means change in dipole moment. If it is not equal to zero, those molecules will give IR spectroscopy or vibrational spectroscopy. We can explain this principle of this IR spectroscopy in two ways. One is classical approach and the second way is quantum approach. In classical approach, the formation of SAEF, stationary alternate electric field. See this is a hydrogen iodide molecule. Hydrogen is very small with respect to iodine. The radius of the hydrogen and the radius of the iodide and mass of the hydrogen and mass of the iodine. So very large. So now let us assume this is M1, this is M2. So now if you send the IR radiation on this molecule, what will happen? This is a polar molecule. Let us assume this is oscillating polar molecule. So now what will happen if you supply the IR radiation on this molecule? It has already dipole moment, permanent dipole moment. Now it will create stationary alternate electric field. These are charged atoms, both are the hydrogen and iodine. Now it will create stationary alternate electric field. Depends on the amount of electric field or quantity of electric field generated on the molecule, it will absorb the energy. Higher the electric field, higher the absorption. Higher the absorption means it will give a good IR peak. This is what the classical approach, and classical approach will be based on stationary electric field formation. Quantum approach, excitation of these electrons within the vibrational energy level. And the quantum approach, we know already the energy levels in molecules, the electronic energy levels. Within the electronic energy levels, we are having vibrational energy levels. Within the vibrational energy levels, we are having microwave. So now we are not showing those electronic and microwave or rotational levels. We are showing only vibrational levels. You see that V0 to V1 at room temperature it will be going. Even at high temperature, what will happen? It is not mandatory. It should go from V0 to V1. At higher temperatures, V1 to V2 or V2 to V3, V3 to V4 also will go. Both are the absorptions only. These absorption capacity or ability we are detecting with the help of our detector, and we are showing it in the form of peak or band. Even they will be naming it as band. Okay, these are the fundamental bands and the hard bands. Since they are coming at high temperature, they are hard bands. Now we know the selection rule and basic principle of IR spectroscopy. Then here we have written FTIR, Fourier transform infrared spectroscopy. Why FT was written, we will let us see in next slide. The first IR source will be there and sample cell will be there. So what will happen? Our sample cell will be having either solid or liquid gas. The IR source, IR radiation will come and it will hit on a sample cell, and sample cell sample will absorb IR radiation, and the transmitted IR radiation or the transmitted rays will be detected by IR sensor. The amount absorbed by the sample will be detected by the detector. We know the initial source, the intensity or the IR radiation, and we'll be determining the transmitted IR radiation with the help of detector. Source for IR radiation, we are having two types of sources. One is Nest lamp and Glober lamp. It's based on SiC, silica carbide. So we are having three types of IR regions. One is near IR, mid IR, and far IR. You see that the energy of near IR is very high, that is 150 to 50 kilojoule per mole, and far IR is very less. And IR detectors, indium, gallium arsenide, this is germanium, lead sulfide, lead selenide, lithium tantalate. These are the sensors or the detectors which will be detecting the IR radiation. So now this is the absorption. This is the raw data. If let us send IR radiation and sample, what will happen? The peak will be like this. So now from this peak, we are not getting any information. Then in UV or most of the cases, if you are unable to observe any information from the peak, we'll be going for either derivative or we will be going for a second derivative to see the changes. Similarly, here we are applying a technique called FT technique, Fourier transform technique. It is based on a mathematical approach. Just we'll be applying the technique, that is Fourier transform technique. Now, if you apply the Fourier transform principle on this sample, so what will happen? This signal will be converting into this form. So now this is known as IR spectrum or FTIR spectrum. Okay, this is the representation of the spectrum. So now what? In y-axis, either we can write absorption or transmission. You see that the peaks are opposite to each other, absorption and transmission. At this point, absorption is very high. It is 95 or 96%. The transmission, just you see that it is an reverse. Since it is absorbing, only transmitted thing is maybe 5% to 3%. That is what these are the different representations of FTIR spectrum. Either we can get absorption versus frequency or transmission versus frequency. Okay. So on the x-axis, we will be having frequency. This is instead of writing energy, instead of writing wavelength, in IR spectroscopy, we will write wave number. That is the, we can represent this EMR, electromagnetic radiation, in different ways, either in the form of energy, either in the form of wavelength, or either in the form of wave number also. At present in IR spectrum, we are representing our the spectrum with wave number. Okay. This is a wave number versus absorption, wave number versus transmission. Now, based on the intensity of IR peak or IR band, sometimes they will name it as band also. So we are classifying the bands or peaks into three. One is weak and medium and strong. See that weak, strong, medium things. Weak means this acetylenic compounds, they will be giving this type of weak bands, and medium and nitriles will be giving medium band or peak. The carbonyls, the carbon oxygen electronegativity difference is very high, then this is a more this group is having more dipole moment. That's what it is giving strong absorption peak. You see that based on this, and this type of, it doesn't have any dipole moment or change in dipole moment. You cannot see this molecule peak in IR spectrum. That means 2-butene won't give IR spectrum. Weak, medium peak and strong peaks will be looking like this, and simple examples are this. Weak means acetylene things, medium nitrile, and strong carbonyls or carboxylic acids and esters. This type of things will give peak, strong peak. And now where this peak will be, that is one more question now. The shape of the band or peak, sometimes the this type of peak we will be observing in IR spectrum or vibrational spectrum. The spectrum will be, now the band is very broad. Okay. The information which we can obtain from FTIR is, it is a destructive instrumental technique, cannot recover the sample, and it will give us a qualitative information, and we can analyze solid liquid gas samples, and majorly we can identify the functional group from FTIR spectroscopy. Similarly, metal ligand complex formation can be, intramolecular, intermolecular hydrogen bonding can be analyzed by FTIR spectroscopy. Okay, and the advantage of FTIR spectroscopy is we can couple it with other equipments like a microscopy, like a TGA, this type of equipments. We can integrate this FTIR instrument into the microscope. That means along with the imaging just at the particular location, if you want to see the IR spectroscopy of the particular location, we can see. That is what the advantage of IR spectroscopy. So now vibrational frequency of the CX groups, this is X, based on the X, just you see here, if X is equal to H atom, this is what it will be. X is equal to O, N, S, this type of thing. If it is there, where will be the frequency and where it will absorb the energy from 3200 to 4000. CH and triple bond from this to this 2000 to 3000 range, this will be happening, and double bond where it will be 1500 to 1800, and single bond, and moreover this 1450 to 400 centimeter inverse. This region is known as fingerprint region, and this region corresponds to bending vibration from 1450 to 4000 centimeter inverse corresponds to stretching frequency, and this region corresponds to change in bond length. This region corresponds to change in bond angle. Okay, change in bond length corresponds to 1400 to 4000, and the change in bond length corresponds to which region? 1450 to 400 centimeter inverse. This is the range of entire organic molecules. The vibrations, is a change in either bond length or bond angle is known as a vibration. If change in bond length is known as stretching vibration, change in bond angle is known as bending vibration or deformation. Sometimes they will be calling it as a deformation. So both are same, bending vibration or deformation. For bending vibration, minimum we need 3 atoms, because it is, if you want to see the bond angle, we need a central atom with respect to 2 bonds. That is what triatomic molecules we can see these bending vibrations, and stretching vibration for any 2 atoms which are equivalent mass or different mass or different electronegativity, we can see this stretching vibration. The classification of vibrations is based on our previous discussion. We are classifying the vibration into 2 types. One is stretching vibration and second one is bending vibration. Stretching vibration will bring change in bond length, and bending vibration will bring change in bond angle. Okay. So now again, the stretching vibrations are classified into two types. One is asymmetric stretching vibration and symmetric stretching vibration. And bending vibration, we are having two types of vibrations, that is in plane bending vibration and out plane bending vibrations. Let us assume these bending vibrations, three atoms are on the same plane, that is known as in plane bending vibration. If within these three atoms, if two atoms are going out of plane, that is known as bending vibration. Okay, this stretching vibration and bending vibration. This we will be discussing now the difference between this stretching and bending. Change in bond length, change in bond angle, that is known as the bending vibration. Again, bending vibrations are classified based on the in plane and out plane. In plane scissoring, this is the scissoring. You see that three atoms are on the same plane, but this is the mode. One atom, two atom, third, like a water molecule. Let us OHH. All three atoms are on the same plane. This is known as scissoring. This is known as rocking. Okay, scissoring and rocking. So now, if you come to the out of plane bending vibration, wagging and twisting. Wagging means two atoms will be going to the out of plane, either this top side or toward my side or your side, just. Okay, this is known as wagging. Twisting means one will be coming up and one will be coming down. This is also out of plane bending vibration. This is known as twisting. Okay, so now the stretching vibration, either it may be symmetric or asymmetric. And one more thing, always asymmetric stretching vibrations are require high energy, and symmetric less, and further the bending vibration. Now see that the bending vibration stretching, we know symmetric and asymmetric. That means one side it will be compressing in a symmetric manner, and asymmetric manner means one side it will be compressing, one side it will be expanding. Like a carbon dioxide, if you take two oxygen atoms, one oxygen atom is expanding, one oxygen is compressing. This is known as asymmetric. Two oxygen atoms are going in symmetric, either expansion or compression. That is known as asymmetric. Okay. If you come to the bending vibration, in plane rocking and scissoring, just you see is an simple an animation will tell us the in plane and out plane bending vibrations. Rocking, scissoring, rocking, scissoring, and wagging, twisting. Okay, these are the four important bending vibrations. So now we want to discuss how many vibrations are possible for a given molecule. Okay, for given atoms it is very easy. We can find out with respect to three-dimensional axis, just x-axis, y-axis, and z-axis. We can keep it as 3n. Okay, for monoatomic things, we can see the possible vibrations or possible these things are, this is a 3n. Let us, if this, let us assume methane molecule, the methane molecule rotation through fixed axis, that is the rotational motion. Then we can see this rotational energy level also in our energy level diagram of the molecules, and movement of molecule from one place to another place, that is translational motion. Okay, translational, rotational, and vibrational. Vibrational means change in bond length or bond angle. These type of motions we are seeing. Just you see that first three possible motions or movements we are seeing for the molecule. One is vibrational motion and rotational motion and translational motion. And here we are not representing the electronic movement, okay, electronic energy level. Here 3 and that is 1. Totally 4 things are there. Total energy will be equivalent to translational, electronic, plus vibrational, plus rotational. So now, the representation of degrees of freedom. It is what is meant by degrees of freedom. Let us, if you want to define a methane molecule in three-dimensional space, we need a minimum number of variables, okay? That minimum number of variables is known as number of degrees of freedom, okay? If you want to define an atom in three-dimensional space, we need x, y, z coordinates. Those are the number of degrees of freedom, okay? So now similarly for molecule also same thing. If you want to define a molecule in three-dimensional space, we need minimum number of variables to define a position of the molecule. That is known as number of degrees of freedom. Or okay, these degrees of freedom of a methane molecule, let us generally we will take it for both the things. So prior to that we will apply for monoatomic thing first. Degrees of freedom for total monoatomic thing we are having only 3, okay, because it doesn't have an 2 atoms. With respect to 2 atoms we can see the different movements, but since it is a monoatomic thing, it will be having only 3 degrees of freedom for single monoatomic. For polyatomic things, for linear or non-linear, it will be having 3n. N is number of atoms. Here n is number of atoms. For monoatomic 3, for polyatomic 3n. So now how many translational motion will be there for monoatomic? 3. Rotational vibrational will be 0 because the monoatomic molecule doesn't have any rotational thing or vibrational thing. If you want to see vibrational, at least 2 atoms should be linked. If you want to see the rotational axis, at least 2 atoms or more than 2 atoms should be present, because if you want to rotate it through fixed axis, it requires either diatomic or triatomic thing. That's what we have mentioned here, polyatomic. For translational, we'll be having 3 for linear molecules. For translational, non-linear molecule, 3 we are having. For rotational, for monoatomic, 0. For vibrational, monoatomic, 0. The same thing, if you come to the linear molecule, translational 3, rotational 2. Because for linear molecule, we have already seen in last class itself, with respect to moment of inertia, we have classified the molecules. Now, if you apply the same knowledge on this, we will be missing one rotational motion, because through this linear molecule, through this axis or through this axis, both the axes are same. Y and Z are same for this molecule, for linear molecule. For non-linear molecule, X, Y, Z will be different. That's what 3 rotational motions we are having. For linear molecule, we are having only 2. They are degenerate, like a Y and Z degenerate. So now we are going to calculate number of degrees of freedom for vibrational, for vibrational mode. So now total is 3n. If you subtract translational, rotational from 3n, we will get vibrational. 3n minus 5. This 3 plus 2 we have to subtract from total. This 3 plus 3 we have to subtract it from total. 3n minus 6. For linear molecule we are having 3n minus 5. For non-linear molecule we are having 3n minus 6. This is what I am telling. Just you see that for rotational motion we are having one rotational axis, and respect to this or this, both are same actually. Either it is vertical or horizontal, Y or Z, we are having only 2 rotational motions. That's what we have written at this point. Rotationally for linear molecule is 2. Okay, translation means end over end rotation. That means molecule will be going out of plane, end over end rotation. Okay, not simple rotation. There is a lot of difference between this motion and this translation motion, because you see that oxygen positions were changed here. Here it was not changed. See this rotational motion, we are not seeing any change. But with respect to this fixed axis, it was. But in translational motion, entire molecule will be moving like through end over end rotation in irregular manner. That is known as translational motion. The fundamental vibrations for linear molecules are number of vibrations 3n minus 5. Number of n is number of signals, or n is number of atoms. Now here we can carbon dioxide CO2. How many atoms? 3 atoms. If you substitute this n is equal to 3, 3 minus 3 into 3 9 minus 5 4. That means 4 signals we will be getting. For carbon dioxide we should get 4 signals. For water molecule we should get 3 signals, because water 3 into 3 minus 6, 9 minus 6 3. Okay. So now what is the importance of this 3n minus 5 and 3n minus 6? It will be giving us the information of the number of signals which we can get from carbon dioxide or water molecule. We can apply this formula for different molecules also, benzene, CCl4, CHCl3, SO2, CO. So we can, n is number of atoms here. N is number of atoms. For linear 3n minus 5, non-linear 3n minus 6. See that what are those? For CO2, carbon dioxide, symmetric, asymmetric, and let us bending vibration we will be. Symmetric stretching, you see, change in bond length is happening in the first case. Change in the bond length is happening in the last case. This is asymmetrical, this is symmetrical. You see that? That is the difference between first one and third one. And the second one is change in bond angle is taking place here in this second vibration, because this is either it is twisting, or either it is an, you see that we are having two types of outplane bending vibrations. Those two outplane bending vibrations are degenerate in carbon dioxide. That's what we are getting, only 3 signals for the carbon dioxide. Let us see here. See here, just 1 minute. Wait for 1 minute. Just. It was enlarged. See here, for carbon dioxide, expansion, both sides, compression, both are equal. That is a inactive. So now, there's a expansion and compression. It is giving a peak at 2565 centimeter inverse, and in plane bending vibration, out plane bending vibration. That means oxygens will be going both outside or upside or downside. So in the last case, one will be up, one will be down. That is what the same things we are written in 2-dimensional here. Finally, we will be getting how many peaks for carbon dioxide? We will be getting only the symmetric, asymmetric, and the bending. 3 peaks the values are this, but for carbon dioxide 2565 and 526, these two only we are seeing in the spectrum. Okay, so now the representations of vibrations for carbon dioxide, these are the representations. One is symmetric, asymmetric stretching, in plane bending vibration, and out plane bending vibration. Totally 4 we are, but there are 3 were identified: symmetrical, asymmetrical, and bending vibration. Bending vibration is 667. Okay, symmetric and asymmetric thing, it will be 2349 is asymmetric and 1388 is symmetric. So really, if you see the carbon dioxide IR spectrum, how it will be, just we will see. Symmetric 2565, symmetric 1480, and bending vibration 5 to 6. 3 peaks we have. Actually, we should get how many peaks? For carbon dioxide, we should get 3 into 3 minus 5. 4 peaks we should get. Only 3 peaks we are getting because this in-plane bending vibration and out-plane bending vibrations are equal. That's what 3 peaks will be. Anyway, this is an inactive thing, but I told you already the induced dipole moment will be there for this symmetric thing, but though it will give a peak at 1388. Normally this is inactive, but if you send the IR radiation on this molecule, what will happen? This carbon dioxide will give symmetric stretching peak at 1388. Okay, 3 peaks for carbon dioxide, and the representation of all the vibrations for carbon dioxide. And for water molecule, similarly symmetrical stretching and symmetrical stretching and in plane out plane vibrations. For water, we are seeing only 3. Those 3, even these 2 will be merged, and we are seeing them as a single broad peak. We cannot distinguish these 2 peaks. That is what the drawback. And even moreover, this asymmetric and symmetric both will be appeared as a single peak. Now for water molecule, how many peaks we are observing? For water molecule, 3 peaks we should get. 3 into 3 minus 6. 9 minus 6 is 3. 3 vibrations means 3 peaks. 3 signals we should get. But how many signals we are getting for water? We are getting for water is only 2 peaks. Just you see that this is the 1 peak and 1 peak is this. Okay. Final for water, how many peaks we are getting? Only 2 peaks. One is at 1594 and 2 is at 3755 and 36. These are simulated values. Don't take this is an experimental spectrum of water molecule. We are having only 2 peaks for water. Okay. And stretching vibration, bending vibration, change in bond length we can be observed in bending vibration. And see the wave number for C single bond C, C double bond C, C triple bond C. What happened to the wave number? It is increasing. Now similarly for CN, C double bond N, C triple bond N, the wave number is increasing. Why it is increasing? If you increase the number of bonds, what will happen? It will be rigid. If it is rigid, if you want to vibrate it, we have to supply more energy. That's what this wave number is increasing. Why the single bond, double bond and triple bond? The wave number is increasing. If you are having, instead of 1 bond, if you are having 2 bonds, molecule or bond will be rigid. If it is having 3, it will be more rigid. See, more rigid means we have to supply more energy. More energy means more wave number. That's what we will be seeing the peak at more wave number, at higher wave number. Okay, similarly for CN, C double bond N and C triple bond N also. And applications of IR spectroscopy, we can identify the hydrogen bonding. Is you can remember any 4 or 5 of these applications. We can find out the force constant. We can find out the mass of the atom also if we know the force constant and vibrational frequency, and inductive effect, hyperconjugation, resonance. These are the electronic factors and which will be deciding the reactivity of molecules. Okay, inductive effect, hyperconjugation and resonance. These 3 things can be determined in IR spectroscopy: hydrogen bonding, intramolecular, intermolecular, and steric factor also. These 3 will decide electronic factor And steric factor also we can. That means molecule, if it is having any steric hindrance, we can identify. And even field effects, phase changes can be determined by IR spectroscopy. Okay. First, factors affecting the frequency. First, determination of force constant. Nu is equal to 1 by 2 pi, the square root of k by mu. Nu is equal to frequency, mu is equal to reduced mass, k is equal to force constant. Nu we can write even, we can write it with a nu bar also. Nu bar means it will, unit will be centimeter inverse. See the force constant and wave number for simple diatomic molecules. Hydrogen, wave number is 4159, and the k value, force constant is k. That k value Newton per centimeter is this much. Okay. For hydrogen 5.2 Newton per centimeter, and for iodine you see 1.7 force constant. Hydrogen force constant and iodine force constant, they are different because mass you are increasing. Mass, if you increase, what happens? It is in denominator. It should decrease. And k versus mu, this it will be having a direct relation. Even k versus mu, reduced mass and mass. You see that vibration, how the hydrogen will be vibrating, how the iodine will be vibrating, and the mass of those both. Iodine 254 I2 and hydrogen 2 grams per mole. We will be having 2 grams of hydrogen. For mole of iodine, we will be having 254 grams of iodine. See, greater the mass, lower the wave number. Okay, lesser the mass, higher the wave number. That means, see that it is vibrating very fast. That is what the meaning. Directly by seeing the formula itself, we can tell the relation between k and nu bar. And here we have written nu. Anyway, how we are getting this equation, that we will see later. From a simple harmonic motion, if you are applying a simple harmonic motion to the diatomic molecule, we will be getting F is equal to kx. K is equal to force constant, that is restoring force. What is meant by force constant here? See that 2 hydrogen atoms are vibrating here. Why this hydrogen atom is, both hydrogen atoms are moving and again coming? Due to the restoring force. That restoring force is known as force constant. That's what, for hydrogen we will be having one force constant, for iodine we will be having one force constant. Okay, for hydrogen and iodine, the force constant or restoring force, if you, these atoms are vibrating, again the molecule will try to get its original position. That's what it's due to the restoring force. That restoring force, or K, that is only known as force constant. Okay. See now, for liquid, water and D2O, the peaks, and now we are seeing the formula of this determination of force constant. Now 1 by nu bar equal to 1 by 2 pi, here nu bar, actually nu bar equal to 1 by 2 pi square root of k by mu. If you simplify this formula, if you apply the, if you square both sides, nu bar square 1 by 4 pi square and k by mu, and we want to find out k, and you send these terms that side. Now what happens finally? K is equal to 4 pi square c square nu bar square into mu. This is what the formula for determination of force constant. Simply just we are having already simple formula, nu bar is equal to 1 by 2 pi to square root of k by mu. So now this frequency and wave number, there is a difference. Just keep in mind, just here it is not a nu, it is a nu bar. We have written in here exactly at this point just. So now theoretically we are going to calculate the force constant by using experimental value. So now what is the formula? K is equal to 4 pi square C square nu bar square into mu. Mu is equal to m1 m2 by m1 plus m2. This is a reduced mass and this is a standard formula. Okay. Nu bar is wave number. Now how they will be giving the problem based on this topic. The wave number or the vibrational frequency of carbon monoxide molecule is 2143 centimeter inverse. Find out its force constant. This is the problem. Now the solution for this problem is in two steps we will be doing. First step is calculation of mu. What is mu? Reduced mass. What is the mass of the carbon? 12. Mass of the oxygen atom? 16. 12 and 16, if you substitute in m1 m2 place, what will happen? M1 m2, 12 into 16 by 12 plus 16, 192 by 28, and this is atomic mass unit. Okay, and this is the unit of reduced mass. Now we have to convert this atomic mass unit into kgs because we are expressing force constant in kg per second square, and we have to convert this atomic mass unit into kgs. 1 AMU equal to 1.66 into 10 power minus 27 kgs. Now if you multiply with this unit, the 6.857 will become 11.83 into 10 power minus 27 kg. Okay. Now the second step, 4 pi square C square nu bar square. 5 value 22 by 7 or 3.14 you can write directly, and 2 times C square. 3 into 10 power 10 centimeter per second. 3 into 10 power 10 centimeters per second. We will be having the unit of centimeter square per second square. Okay, that you keep in. And here 2143 centimeter inverse, 2143 centimeter inverse. The centimeter square and centimeter inverse square both will be cancelled. Finally what we get? Kg per second square. Okay, if you calculate, if you do it, we will get this value. The value is 1855 kg per second square or Newton per meter. Okay, both are same actually. Okay, kg meter per second square is Newton. In that case, kg per second square is Newton per meter. Okay, the force constant K equal to 1855 into kg per second square. This is what determination of force constant of carbon monoxide.